Okay, the next thing I want to look at is the periodic trends of the periodic table. So how do the rows and the columns lead to different trends? Okay. All right, so the first one we'll look at is atomic radius versus atomic number. And the rule is that as you go across a row, the smaller the size. And so this is showing the row from sodium to argon. And you see that the atomic radii goes down as my atomic number, which is the x-axis, goes up. The second part is that as I go down a column, the larger the size. And so this is showing group 1. This is lithium, sodium, and potassium. And you see that this being the radii, the radius gets bigger. And it doesn't matter, this was the group 1s. If I look at the noble gases, they still go up here also. Neon, argon, and then krypton. It's just not quite as good a trend the further down I go. All right. If I look at the representation of the atomic radii, okay, you see here that as I go across the row, from lithium to neon, they get smaller, okay? But as I go down the column, and it doesn't matter again if I do the 1As or if I do the 8As or something in the middle like 4A, as I go down the column, the size gets bigger, okay? So why does that happen, okay? And it happens because something called effective nuclear charge. Inside the nucleus, you have a positive ion, or positive charge. That's what protons are. And as I go across the periodic table, go back up here, as I go across the periodic table, you notice that my number of protons goes up. Okay, so this is 11, this is 12, oops, sorry, I'm still learning how to use this. Where am I at? This is 12, this is 13, okay? And so by element number, these are also the number of protons. So it's becoming more positive as I go down the column, okay? So erase all that. The extra scribbles. So the positive charge that the electron experiences from the nucleus is equal to the nuclear charge but reduced by shielding. So I like to look at this as being the rows, okay? If I were at this baseball stadium, which this looks like it's in New York, I don't know which New York team, but it's New York, okay? If I'm sitting here, okay, there is no other people in front of me. I have a clear view of that, okay? But what happens on the periodic table as I go across, if we imagine this being the nucleus, okay? And so basically, as I go from here to here to here, basically the baseball field is getting bigger. My charge is getting larger. So therefore, it looks like I'm closer and closer. Inside the atom, it actually becomes closer and closer and closer. Now, what happens instead when I move back, okay, so I go from here to here, okay, from here to here, then what happens is that the screen or the baseball field has gotten bigger, okay, but now I have a person who's blocking me sitting directly in front of me. And then the same thing happens as I go across this row. Okay, so as I go across this row, this becomes, still the screen gets bigger, but I still have that front row. And as I continue to go back in the stadium, okay, I have more and more people sitting in front of me. And I'm short, I'm short. Okay, so while I may be able to lean right here to be able to see past somebody, then this person is going to be blocking me, or this person is going to be blocking me. Okay, and so that's what screening is happening, is that the field's getting bigger, but I'm having more difficulty seeing because I have more things. So if I look at a version of the atom, okay, and this is simplistic. Do not draw this as an orbital diagram. Okay, I have my nucleus. here. And then I have my first row, which only has 2 electrons in it. 1, 2. Okay. And then I go to the next row. Okay. It's further back, but my nucleus keeps drawing every time I go here. But when I go through here, this electron is being screened because remember these are in constant motion. These 2 is being screened by there. But every time I add an electron here, this nucleus gets more and more positive. So it's basically like a magnet. This magnet becomes larger, and these magnets are all the same size. It feels a greater attraction here. And so every time I add this, going across a row, okay, then it becomes bigger and bigger and bigger, and these 2 electrons are still the same one screening it. So as I go across the row, the atom becomes smaller and smaller because there's a greater attraction between the positive nucleus and the outer electrons. And a positive and a negative attract each other. Okay? Okay? So that's what effective screening is. Oops. Alright. So it wants me to rank the following according to I rank the following according to the atomic radius. So I have carbon, I have aluminum, and I have potassium. Okay? So it wants an increasing size. So which one of these 3, oh, I missed oxygen, and oxygen, which one of these 4 has the smallest atomic radii? Okay, the further up in the periodic table it is, the smaller, and so that leaves me between carbon and oxygen. Okay, and the further to the right that I go, then the smaller it is. Okay, so oxygen is going to be first, it's going to be the smallest, followed by carbon because they're on the same row, and then I'm going to go to aluminum, and then I'm going to go to potassium. Okay, and that's all you have to do for that problem, is rank those. Now, you do have to pay attention to the word, okay? Is it increasing or is it decreasing, okay? So if it's increasing, I want the smallest first to the largest, but if it says decreasing, then I want the largest first going to the smallest, okay? All right, the next trend we'll look at is ionization energy. Ionization energy is the energy it requires to take an electron away from an element, okay? So, what do you think is easier? Which is easier? To remove an electron? To remove an electron. Metal or non-metal? Oops. All right. There we go. All right, metal or non-metal. So basically, to remove an electron forms what charge? That forms a positive, right? So that's a positive ion. Okay. So think about it. Which one tends to form positive ions, metals or nonmetals? And the answer is metals. So metals have a lower ionization energy than nonmetals. It's easier to remove that electron from the metals. And so I see that here. If I look, I have lithium, sodium, potassium, rubidium. Okay? And so the metals are down here at the lowest energy. My noble gases of helium, neon, argon, krypton are higher energies. Now, let me erase all this. Oops. Because now, okay, as I cross a row, okay, so from cross a row means from left to right, I increase the energy. Okay, so it becomes harder to take an electron away as I go from the metal to the non-metal side. And as I go down a period, it decreases energy. So the further away the electron is from the nucleus, the easier it is to remove it. And so I have argon, krypton, and xenon. You even see that to some extent, but less of an extent. Here's sodium, potassium, and rubidium. It's just not quite, because they're all metals, they all lose their electrons easily. It's harder to see that one. Okay, you can see it in the noble gases, however. In fact, xenon is the only noble gas that will actually form compounds, and it only does so with fluorine. Okay, so it wants to know, circle the atom from each pair that has the greatest ionization energy. Which one is it harder to remove an electron from? Okay, so figure out where I am. Okay, get closer. Okay, I have lithium and beryllium first. Okay, so as I go across the row, it becomes larger or harder. So therefore, beryllium is the largest one. Okay. All right, now I look at sodium versus potassium. As I go down the column, what happens? It becomes easier to remove the electron as I get further away. So therefore, it is potassium. Okay. Next one is chlorine versus silicon. Okay. This one's on the same row. So chlorine is the hardest. All right. Calcium or barium. I still want to use this thing as a mouse instead. All right, same column. So the further down a column I go, so therefore it becomes barium. And the last one, phosphorus or argon. Again, the same row. Further over I go, the harder it becomes, so it is, argon. Okay. All right. Now, I have second, third, and etc. ionization energies. Okay. So here I have ionization energy, first, second, third, fourth, fifth, sixth. And basically this is element 1, 2, 3, 4, 5, 6, 7, 8, and 9, and 10. So basically these are the first 10 elements of the periodic table. If I look, this is a 1s1. I only have one electron to lose, so that's why there's only that. This is a 1s2. Okay? And so you can see here I only have 2 electrons to lose, and they're both in the same thing. This one becomes a 1s2, 2s1. And you see here, if it's going to, so this right here is considered to be the core, whereas this is the valence. And so you see here the jump, because it goes from 520 to 7,000. That difference right there is greater than times 10. Okay? And then to go from here to here, and that's what I'm basically looking at, is I'm looking at the difference. This is less than times 2. So wherever that big jump is, where 10 versus 2, is where I'm going from being a valence electron to a core electron. Okay? So let's look at the next row. All right, beryllium is 1s2, 2s2. So I have 4 total electrons here. Okay? This difference is basically times 2, approximately. This difference is times roughly 13. This difference is like times 1.5, less than 2. Okay, so where do you see that big jump, 2, 13, or 1.5? And the answer is 1.3. So to go from the second to the third, if I look at this, again, this is my valence electrons, which I'm going to abbreviate VE, and these are my core electrons, or CEs. So to go from taking 2 electrons to taking the third electron, so by looking at a series of ionization energies, I should be able to tell or predict how many valence electrons I have. Okay, and so that's true as I go down, say, to oxygen. Oxygen is 1s2, 2s, 2s2s, 2p4. Okay, and so again, this is times 2. This is approximately times 2, and this is just rough approximations. This is more like 1.5. This is about 1.5. I'm not going to get exact. This is less than 1.5. And then this 13 goes into 71 about times 8. Okay, just approximate. Probably closer to 6. We'll say 6. 6. Okay, so if I look at these differences or multiplications here, okay, the one that's great is 6. Okay, and that's where I went from the 6th electron to the 7th electron. So my 6 are my valence electrons, and then I have 2 core. It doesn't go all the way back to 8. Okay, so what would I do with this kind of question? Okay, if I gave you, okay, so a series, and the book doesn't have any examples of ionization energies, which I'm going to abbreviate IE. I'm going to just make these up. Okay, I'm going to say that, of course, as I go down the column, it gets smaller. So if I have, say, 300, 350, say 500, let's say 700, and then 5,126, and then say 9,433. How many valence, based on this series of ionization energies, how many valence electrons do I have? Okay, again, looking at the difference there, that's less than 2, this is less than 2, and this is about 8. Okay, so looking at the difference here, this is less than 2, this is less than 2, this is approximately 8, this is less than 2. Okay, so I would say that I have 3 valence electrons. And that's what I'm basically saying, is that you can predict how many valence electrons there are based on the jump or the size of the ionization energy. Okay? Like I said, the book doesn't ask any questions like that, but I like to make that point. The last trend is the electron affinity. We're not actually going to do any problems like that at all. Electron affinity is the energy to add an electron to a neutral atom. The more negative the number, the more stable the ion is. So in general, left to right, more electron negatives, bottom to top is more electronegative. So I want to go back and kind of recap here. Finally, for atomic radii, okay, it decreases left to right. And it decreases, I'll write them so they're both on the same thing, bottom to top. Okay. For ionization energy, IE, because it's just easier, okay, it's the opposite trend. From size. or radii. Oops. Which means that it decreases right to left. By the end of the semester, I should be really good at this. And it decreases top to bottom. So they're opposite trends. Okay. And that is actually all we're going to cover in this chapter. It's not quite the end of the chapter, but that's all we're going to cover in this chapter. Thank you.